So when we talk about electrolysis, we are now considering non-spontaneous redox reactions. So when you have a cell set up and this is connected to a voltmeter and your voltmeter gives you a negative reading, then the redox reaction of that cell is non-spontaneous in the in the direction written in your chemical reaction, which means your reactants do not form the products. However, if you create a cell wherein the reaction is reversed, so you have the products becoming the reactants and the reactants becoming the products, that will give you a positive cell potential of the same magnitude. Okay, so that's one important fact about your redox reactions, about electrochemical reactions. Okay, so for example, if we have this reaction between solid zinc and copper ions, so forming solid copper and zinc ions. Okay, so this is the reaction of this electrochemical cell. So the voltmeter gives a positive reading. So it means that this reaction is spontaneous. But if we make an electrochemical cell wherein the reactants are solid copper and zinc ions, and the products are solid zinc and copper ions, this will give you a cell potential of negative 1.103 volt. So which means this reaction as written, so from reactant to product, this reaction is non-spontaneous. It will not take place unless you connect it to a battery. So the reverse is spontaneous. You don't need to connect your electrochemical cell to a battery for this reaction to take place. The reverse is non-spontaneous. So again, if you have a cell potential that is positive, the redox reaction is spontaneous. What you have is a galvanic or voltaic cell. It produces electricity. But if your cell potential is negative, the redox reaction is non-spontaneous. Your electrochemical cell is classified as an electrolytic cell. For this reaction to take place, it needs an external source of energy, typically a battery. And if you connect it to a battery, then this redox reaction will take place. Okay. So, let's discuss electrolysis. So in electrolysis, there are some factors that you must consider if you want to perform electrolysis. So electrolysis is the reaction taking place in an electrolytic cell. Electrolysis. So in my previous example, so we had this, okay? So this is non-spontaneous, which means solid copper cannot displace zinc ions. But if you want to recover the zinc ions as solid zinc, then you can set up this cell, connect it to a battery, and allow electrolysis to take place. So what you are doing is that you are electrolyzing zinc because it's the one that turns into solid. Okay, so you are electrolyzing zinc. The thing is, one of the questions that we need to answer is, what should be the voltage of the battery that I will connect to this electrochemical cell? Ano dapat yung voltage niya? Is it enough for me to connect a battery that will provide 1 voltage? Will I get my solid zinc if I connect the cell to a battery whose voltage is 1? The thing is, no. So you have to consider this cell potential. So the voltage that you must supply must be a bit above this cell potential. So if I connect a battery that will provide 1.5 voltage, then probably I will get solid zinc. However, that's not the only factor that you must consider. So another factor that must be considered is what we call overpotential. So overpotential is an excess of voltage that may be necessary to cause a particular electrode reaction to occur. So typically, this overpotential is more prominent or has a higher value in electrolytic reactions involving gases. Because since gases are more relatively mobile, so um, they have a greater distance between the electrode of your cell, right? Kasi nga gas sila. So you have to provide this additional potential just for the gases to have considerable interaction with your electrode. Hence, it will assist your electrolytic reaction. That's your overpotential. Next thing to consider is that there might be competing electrode reactions. So for example, if we are electrolyzing sodium chloride, so what's happening to sodium chloride? Sodium will turn into liquid sodium and chloride ions will turn into chlorine gas. That's what happens if you electrolyze sodium chloride. So if you have molten sodium chloride, okay, so it's just solid sodium chloride melted, pure sodium chloride melted, then you won't have any competing reactions. Your sodium ions will simply be reduced to liquid sodium and your chloride ions will simply be oxidized to chlorine gas. However, if your sodium chloride is dissolved in water, so you have aqueous sodium chloride, right? And this is the one that you will electrolyze instead of molten sodium chloride, then there will be competing reactions because water can be reduced to hydrogen gas. Water can be oxidized to oxygen gas. So the presence of water complicates the scenario. Kung molten sodium chloride siya, there's no problem. But if it's aqueous solution of sodium chloride that you will electrolyze, you have competing reactions. Now, let's take a look at their reduction potentials. Okay, so for the reduction of sodium ion, we have 2.71 volts, negative 2.71 volts. For the reduction of water, we have negative 0.83 volts. Now, since the reduction of sodium ions require a higher voltage, kasi kailangan mo ng at least 2.79 volts just for this reduction reaction to take place, then if you connect it to any battery, most likely, yung reduction ni water ang mangyayari. Unless you connect it to a battery that, let's say, 9-volt battery, then pwedeng mangyari yung reduction ng sodium ions. But if you connect it to, let's say, your typical AA batteries, which has a voltage of 1.5, then hindi niya kayang suportahan yung reduction ng sodium ions. So ang reduction reaction lang na mangyayari ay yung sa water. So okay na-eliminate na natin yung reduction ng sodium ions. How about oxidation? So there are two possible oxidation reactions, right? So let's take a look at the overall reaction. So ang pagpipilian na lang natin yung dalawang reduction. Kasi ito na-set na natin na reduction ng water yung most likely mangyayari. Kasi mas mababa yung absolute cell potential niya. So if we combine it with the oxidation of chloride, so this is the overall reaction. And this is your cell potential, negative 2.19 volts. And if we combine the reduction of water with the oxidation of water, this is the overall cell potential, 2.06 volts. So we see that their cell potentials are comparable, which means most likely you will get a mixture of, aside from hydrogen gas from the reduction of water, you will get a mixture of chlorine gas and oxygen gas sa products mo. Meron ka ring chlorine at oxygen. Kasi nga, magkalapit lang yung potential. Right? But, the thing is, again, going back to the first factor that I mentioned, which is overpotential, okay? Oxygen gas has a higher overpotential than chlorine gas, if I remember correctly. Which means, most likely, ang mangyayaring oxidation reaction ay yung oxidation ng chloride ions instead of oxygen ions. Okay, so due to the higher overpotential of oxygen gas, most likely, ang products natin would be composed of hydrogen gas and chlorine gas. Majority ng products, hydrogen gas and chlorine gas. You will probably get some oxygen gas pero sobrang konti lang. Okay? Now, aside from those two factors, yung overpotential and yung competing electrode reactions, there's also the fact that your reactants are not in their standard states. So this also affects your cell potential, the calculated cell potential. So, for example, in typical industrial electrolysis of sodium chloride, the concentration of your chloride ions is 5.5 molar. It's not 1 molar. So the potential is 1.31, not 1.36. So ito, yung sa oxidation ng chloride ions. This is 1.31, not 1.36. Another factor, for example, is the pH of your solution. So in the industry, the pH that they use is 4. So the potential of water oxidation, this one, is not 1.23 but 0.99. Kasi kung standard state yan, the concentration of your hydrogen ions should be 1, which gives you a pH of 0. But they use pH 4. So the actual potential is not 1.23 but 0.99. So you also need to consider factors like this if you are performing industrial electrolysis. Para saan ba yung industrial electrolysis? Ayun nga, para ma-recover natin yung mga elements. That's the number one objective of industrial electrolysis, right? Katulad nito, meron kang sodium chloride, then you can recover pure sodium and pure chlorine gas. Okay? And finally, the nature of the electrodes that you use is also important. So, if you don't want additional competing electrode reactions, then you should use inert electrodes like platinum. Kasi for example, kung gumamit ka ng active electrode like silver, for example, like, right, silver typically undergoes reduction or oxidation reactions at very low voltage values. E di may additional competing reaction ka. Okay? So that's the qualitative aspect of electrolysis. So again, anong objective sa electrolysis? To recover pure elements via redox reactions. So these involve redox reactions that are non-spontaneous. So you supply electrical energy to the reaction so that the redox reaction can take place. Now let's go to the quantitative aspect of electrolysis reactions. So the important thing you have to remember here is the mole of electrons. Because once you are able to determine how many mole of electrons were involved in the electrolysis reaction, then you can relate that to the amount of product that you can recover from your electrolysis reaction. So moles of electrons is related to your current and how long you perform your electrolysis reaction. So the formula is given as moles of electrons is equal to current times time all over your Faraday's constant. Okay, so how do we use this reaction or this equation? So for example, we have electrodeposition of copper. So you are electrolyzing copper from a certain sample. So gusto mo lang makuha yung copper. So you want to deposit just copper. So the sample is dissolved to produce an aqueous solution of your copper ions. This is the one that you electrolyze. So at the cathode, your copper 2 ions get reduced to solid copper. So yun, nagkaroon ka na ng pure copper, right? So the question is, what mass of copper can be deposited in 1 hour by a current of 1.26 amperes? So remember class, current has units of coulomb per second. Coulomb per second, that's why we will multiply it by time just to get coulombs. And then by dividing it with Faraday's constant, you end up with moles of electrons. Okay, so first we need to get moles of electrons. So current used is 1.26 amperes or 1.26 coulombs per second times 1 hour or 60 seconds divided by Faraday's constant, 96,485 coulombs per mole. So this will give us a value of 7.83541 times 10 raised to negative 4 mole of electron. Now, according to the reaction, there are 2 electrons involved per mole of copper solid being deposited. So we are looking for the mass or how many grams of copper that can be deposited given these conditions. So we have 7.83541 times 10 raised to negative 4 moles of electrons. So 2 moles of electrons is equivalent to 1 mole of solid copper. And then using the molar mass of copper, which is 63.5 grams per mole, we get 0.02488 grams of copper. So this is the mass of copper that we can okay, wait, I missed one conversion here. So 1 hour is not equal to 60 seconds, rather it's equal to 3,600 seconds. So ayan, diniretso ko kasi instead of writing it one by one. So that's 1.26 amperes or coulombs per second times 1 hour. And you have 60 minutes in 1 hour. And you have 60 seconds in 1 minute. So this is not the correct moles of electrons. Okay, so that's 1.26 times 3,600 divided by 96,485. So we get 0.047012 moles of electrons. So multiply that or divide that by 2 and multiply it by the molar mass of copper. So we get 1.4926 grams of copper deposited given these conditions. Okay, so this is how we use this formula for electrolysis reactions. So you see here, di ba, nare-recover natin yung pure element. Okay, let's try this time with a gaseous product. Okay, so for this problem, the electrolysis. Okay, for how long would the electrolysis in the previous problem have to be carried out using platinum electrodes and a current of 2.13 amperes to produce 2.62 liters of oxygen gas at 26.2 degrees Celsius and 738 millimeters mercury pressure at the anode. Okay, yung previous problem, so ito yung tinutukoy niya, right? This time, gumamit ng platinum electrode. So you have platinum electrode, which means you don't have the solid copper. So hindi ka mag-electrolyze ng solid copper. What you want to do is you want to electrolyze water. Okay, para makuha mo yung oxygen gas. So that means what's happening is that water is being oxidized into oxygen gas. So the balance reaction for this one is being oxidized, right? So that's 2H2O plus 4H plus 4 electrons. So this is the balanced half reaction for the oxidation of water to oxygen. Okay, so the conditions are you have 2.13 amperes. Okay, it's asking for the time. So since it's asking for the time, we have the target amount of the product, so we can get the moles of electrons. Okay. So how do we get the moles of electrons? First, we need to get the corresponding moles of oxygen gas muna. So, moles of oxygen gas, I want to draw moles of oxygen gas is equal to, we are given the volume, the temperature, the pressure. Anong equation kaya yung gagamitin natin para makuha yung moles ng gas? It's PV equals nRT, your ideal gas equation. Okay, so we are after N. So that is pressure, 738 millimeters mercury converted to ATM. So the conversion is 760 millimeters mercury is to 1 ATM times the volume in liter over the temperature, the gas constant first, 0.0821 liter atmosphere per mole per Kelvin times the temperature, 26.2 plus 273.15 Kelvin. Okay, so moles of oxygen is equal to so we have 0.103519 moles of oxygen. So this means how many moles of electrons were involved in this electrolysis reaction. So according to our reaction or balanced half reaction, for every mole of oxygen, you have 4 moles of electrons involved. So we need to multiply this by 4. So we have 0.41407775 moles of electrons. So now we can finally use the formula. So the formula was moles of electrons is equal to current, that's amperes times time over Faraday's constant. We want to compute for time. So time is equal to moles of electrons, 0.41407775 moles times Faraday's constant. That's 96,485 coulombs per mole divided by amperes or 2.13 coulombs per second. So we get 18,756.93 seconds, or let's convert this to hours, maybe hours. So to convert this, we divide this by 3,600 seconds in 1 hour. So we get 5.2 hours. So you need to perform the electrolysis reaction for 5.21 hours to get 2.62 liters of oxygen gas using 2.13 amperes of current. So this is how we quantify our electrolysis reactions. And with this, I would like to end this lecture video, and we will continue practicing solving these problems, doing some analysis in our next session.